All right, guys. There we have our question paper, April 2019, which is an X paper. As we are revising towards our exams, you are supposed to understand the questions, how they are given at the end of the day. You need to know the typical questions, because if you check Mechanotechnics, is just a repetition throughout. So once you know the idea of answering a question, you are good to go in each and every question. All right, so we're not going to waste much time. Take note, we are given to answer all of the questions, answer all questions carefully, and number the questions according to the numbering system used in this question paper. Sketches must be large, neat, and fully labeled. It is try to have something that is clearly presented. That is what they are trying to say there. All right, so not going to waste much time. We're just going to quickly check our questions, how they are given. You are supposed to understand the concept of your questions, like I said before. So we've got questions that are under the theory part, where you need to know your theory, understand your diagrams, right? The sketching of your diagrams, the explanations, the explanation, that is the part of what? Your theory. As long as you are dealing with theory, they need to know, they need you to perfectly explain whatever that is needed in point form. All right, just write your answer direct. If there is a specific question that is required, answer your question direct. All right, so like I said, I'm not going to waste much time. Let us quickly check the first question. So we are given on 1.1, that is what is meant by individual production, and individual production, and that is 3 marks for that. All right, so like I said, they just need you to be straightforward to the question. So I just want you to see this part. I just hope you're going to be able to see this part. All right, guys. So this is what I'm having for the individual production. With individual production, you concentrate all manufacturing process efforts on one item. Workers complete all operations on this single item before they start working on the next. That is a single production. All right, then the other part, now they want you to give or to list examples where the individual production method could be applied. Where is it that we can use this individual production? Where exactly can we have this application? So we can use this in manufacturing a boiler in a workshop, where one item can be made at a time. All right, or we can have this when a workshop is instructed by a client to cast or machine a special casting. It can be like that. Then on that condition, you just have to focus on one thing or to focus on one production. On 1.3, they want us to name 5 characteristics of individual production. The one that we've been saying, that we are focusing on the producing of only one item at a particular time. What is it that we are considering as the characteristics? How do we see it? All right, so it has got only one product is produced at a time, like we said before. From this part, remember, we have been talking about only a product, a single product being manufactured. So this is the same concept that we have. All right, specialized equipment is used. The layout is flexible. The capital outlay is extremely high, and also the workers are flexible and highly skilled. Remember, they are just focusing at a single thing at a single time. So they are having the required knowledge for that. All right, it increases it increases the chances of that knowledge. All right, focusing or concentrating on one thing. Name 5 ways in which a roller bearing can be damaged. All right, remember, they can be damaged depending with the lubrication. If this lubrication is excess, like what we have on this first part, the excess of lubrication, the mounting the bearing the wrong way. If you mount it in a wrong way, then it can be damaged. All right, mounting the bearing in a damaged housing or shaft, applying force to the wrong ring during mounting, and also misaligning the bearing during mounting, and also mounting the housing or cover incorrectly. All these, they can enable our bearing to be damaged. All right, so that was the condition of our question. And 1.5, make a labeled sketch of a siphon wick lubricator, which can be used for oil lubrication of machine part. All right, remember our siphon is like this. All right, let me just try and show you the diagram. It's just a simple sketch here that we have where you're supposed to show the oil container, the wick, and also the container that has got what? The oil inside of your what? Inside of your container. That is the most important part there. Just that. So that's it. Make a labeled drawing of a deep painting method. Actually, when we are dealing with the workshop practice, the part of workshop, guys, I think I'm gonna need time to talk about this. All right, I'm gonna need time to talk about this in terms of our diagrams and so forth. All right, so this one, given the direction of flow, the conveyor belt, the components, that is the vapor cleaning liquid, negatively charged paint, then the brake oven and so forth. So like I said, I'm just gonna need time so that I will give you at least what is needed in your syllabus, like exactly what is needed in your syllabus in terms of your workshop practice. All right, the part of the workshop that can help us a lot. All right, so on this part, they want us to state 5 disadvantages of what the deep painting method. Remember, we had a deep painting method that we explained before. Now they want methods, the disadvantages there, which is excessive use of paint, large quantities of paint are kept in paint deep troughs, then also loss of thinness through evaporation. Then only for mass production, is just we need it when there is a mass production only. Like we can't do it when we want just 1 or 2 things. We need it when it is for mass production. If paint is left in deep troughs overnight, continual through agitation is needed the following day. So you see, there's a lot of work there. There is a lot of work. So that is what are the disadvantages. So when you're asked about the disadvantages, that is what they expect you to list or to talk about. Okay, so that was 30 marks, just like that, 30 marks, guys. So you see your theory part is very, very important to understand it or to know it. As we can see, it is an advantage to know your theory. All right, then we move on to this part whereby we are working with our belt. So these are we are given the driving pulley of a V belt. So if the major part that I actually took this question paper, it was because of the error on the answering of this question. This is a V belt that we are working with. All right, we are dealing with a V belt. So we are going to see that in our calculations, the V belt, it has got its own specific calculations that are necessary, that are different when you are working with a normal belt, which is a flat belt. All right, when you're dealing with a flat belt, there are things that you need to know. When you're dealing with a V belt, there are formulas that differ here and there. All right, let us talk about this. We are given that it's a V belt and it has got an effective diameter of 250 millimeters. So that's our effective diameter, and a speed of 1,800 revolution per minute. All right, so let us check our information here. That's question 2. All right, so we have got the first thing that is a given as a V belt, and we are given the effective diameter of 250 millimeters in meters divided by 1,000, that's 0.25, and also the speed of 1,800 revolutions per minute. So this is revolution per minute. That is what we have in this case. And also take note, the angle of the V groove of the driving pulley is 46 degrees. This is the angle of the driving pulley. And remember, when you're dealing with a V belt, you're gonna need alpha, which represents at the half groove angle. So alpha is the half groove angle. So you divide this by 2, 46 degrees divided by 2, which is 23 degrees. So we are saying this is the half groove angle. So you have to divide by 2, which is 23 degrees, and it must be in degrees, all right? Alpha is taken in degrees. I'm going to show you the formula where you use this alpha. So remember when you're dealing with the ratio between T1 and T2, okay, we shall talk about that. Then we are given the contact angle of the belt of 160 degrees, which is theta, and theta is supposed to be in radians. Our contact angle, theta, is supposed to be in radians. How do we convert degrees to radians? We divide by 57,3. So this will give you 2,792 in radians. So that's our contact angle, this one. Do not forget, we've got the contact angle, and this one is our half groove angle. So it's the half groove angle. All right. So that is the idea there. Then we are given the coefficient of friction of 0,3. The mass of the belt is 0,5 kilograms per meter length. All right, so there are two things that we are given there. One, the coefficient of friction, which is 0,3. Then we are also given the mass. Take note, the mass per meter length. That's 0,5 kilograms per meter length. Whenever you are given the mass per meter length, I want you to be careful. This is the part that I was saying our question paper had a mistake or an error when answering this question. Whenever you're given the mass per meter length like this, you are supposed to find the centrifugal tension, which is TC. Since TC is involved with the mass per meter length times what? The velocity squared. So once there's mass per meter length, then you're supposed to have TC. But if you are not given the mass per meter length, there is no need for us to use TC in our ratio between T1 and T2 for our formula. You have to be careful. And also when we are dealing with a V groove, the angle has to be included, the half groove angle, the one that we divided by 2, it must be there. It must be there. So you must be careful on that part. Okay, so the question was calculate the number of V belts required for this drive if the maximum allowable tension per belt is 900 and also it has to transmit 30 kilowatt. Okay, let's take this. We need the number of V belts. We're just going to name them this, just going to call them N. We do not know this, the number of V belts. All right, so we do not know this, the number of V belts. But we are given there that the tension, which is the maximum allowable tension, this is your T1, the maximum allowable tension is T1, which is given as 900 Newton. And also we are given the power of 30 kilowatts. And they are asking us to calculate this, the number of V belts. How so? How is it this possible? For how many marks? For 14 marks. Okay, let's see. This is it, guys. As long you are dealing with your belt drives, like I said before, it is just the formulas. You need to connect your formulas properly. All right, so our memo, it was actually an error, this one, because they did not consider a lot of things. So no problem. Let us try to work on this. Remember that if you are dealing with a V belt, this is one thing that you need to consider. For a V belt, and we are given the power. Remember, we are given the power there. We know that the power is equivalent to the effective tension times the velocity times the number of what? The number of V belts. So this is the number of V belts, which is N. There we need the velocity. We do not have the velocity. We need the effective tension. We do not have this effective tension. We just given T1. But we know that the effective tension, which is TE, is the difference between T1 of the tight side minus T2 of the slack side. That is what we know. But we are limited. We do not have anything that has to do with T2. Also with TM. Okay. Let us think about where this is found and also this is found. Both are found on the ratio between T1 and T2. Remember that the ratio between T1 and T2 was supposed to be like this. T1 over T2 is equal to e to the exponent of micro theta, the cosec of the cosec of alpha for a V belt. That was supposed to be the formula, but because you are given the mass per meter length, that means we are supposed to have what? The centrifugal force there. And once the centrifugal tension is there, which is our centrifugal force is there, the formula is no longer like this. The formula now is going to be like this, T1 minus TC, everything over T2 minus TC is equal to e to the exponent of micro theta, the cosec of alpha. Take note, where this is a coefficient of friction, the angle of contact, the half groove angle in degrees. So this is it. We can find this because we do not have this, so we can determine this. All right, I think that is the only thing that we need here. Everything is there. So let us find this. But before that, let us also, we can make this the subject, T2 the subject of the formula. We can make that the subject. All right, let us just make this the subject once and for all. Then I'm going to come back here to calculate this. But let us just make this the subject because we are going to need T2. So just make T2 the subject. This is over 1. So if I cross multiply, that's 1 times this. This will be this times this. This times this. Take note, this times this. So it's going to be T2 minus TC into e to the exponent of micro theta cosec of what? Of alpha is equal to 1 times this. So that will be T1 minus TC, like this. Okay. So what does it mean? It means I can divide by this. Remember, I want to find or to make T2 the subject. So I can divide by this, e to the exponent of this, both sides, e to the exponent of this, both sides. All right. So without wasting much time, we know that e to the exponent of whatever that you're going to divide is going to cancel this side, and you remain with T2 minus TC is equal to what you divided here is going to be T1 minus TC like this over what? We divided by this e to the exponent of, that is e to the exponent of micro theta cosec alpha. All right, so transpose this to the other side, we have T2 as the subject. So therefore, T2 can be calculated as this part that we already have, T1 minus TC as it is. So just going to rewrite this part as it was, e to the exponent of micro theta, the cosec of what? The cosec of alpha in this case, which is our half groove angle. Like I said, we need to transpose this TC to the other side. So the moment we transpose it on that side, it will be plus TC. All right, so this is the formula that we are going to use to find T2. Like we said, we need T2. But we do not have TC. So where are we going to have TC? Let's go back here and calculate our TC. Remember, I said here, TC is equal to mv squared. But still, we are limited there because we do not have V. All right. V can be calculated from which point or from where? From the formula. Remember, V is equivalent to, let us calculate the velocity. So calculate the belt velocity. So you're going to calculate the belt velocity, which is V. Remember that V is equivalent. If we are not given the belt thickness, we do not have the belt thickness. So it's going to be pi dn over 60. We're given this in revolutions per minute. We're just going to use capital letter N. I don't know, whatever that you understand, but that's pi dn over 60 in what? Meters per second. But this is in revolutions per minute. So like I said, you do not have the thickness of what? Of the belt. Once you are given the thickness of the belt, the formula is going to be V is equal to pi d plus the thickness. So you're going to have the thickness of the belt times N, which is this N in revolutions per what? Per second. So you have to change this to revs per second. So we do not have the thickness. So that means this formula is not valid. This one is not going to work. We are going to use this formula that we are having in the first place. So that means by substituting, we can calculate our V that is pi times the diameter, this diameter that we are given in meters, all right, which is 0.25. So that's 0.25 times n in revolutions per minute, 1,800, everything over 60. This will give us the velocity in revolutions, in meters per second. This is in meters per second, guys, all right? So that was going to give us 23,562. Just also cross-check with your calculations, meters per second like this. So with this velocity that we are having here, we can use it now to calculate our centrifugal tension. As I said that the centrifugal tension is equivalent to this formula. So we can calculate this. All right, so let us calculate our centrifugal tension, guys. Very sorry for this. I'm just going to use this space. So the centrifugal tension, TC, is mass per meter length that we are given times V squared, which is our velocity. So that's TC as the mass per meter length. We are given this, the mass per meter length, 0.5. We calculated the velocity, that's 23.562 squared, V squared. So thus, we are going to have the centrifugal force of 277.584 in Newton. As long you are given the mass per meter length, you are required to have this. You are supposed to have TC. Do not say, because I'm not given TC, so I'm not going to use it on the formula. No. As long you are given the mass per meter. But if you are not given the mass per meter length, therefore, there's no way, because the centrifugal force is calculated from where? The mass per meter length. So now that we have this, we're just going to substitute. Remember, already we made a formula for T2. Why do you want T2? Because it's the one that we need here for the effective tension. TE is T1 minus T2. So like I said, we are going to need T2 here. That's why we made T2 the subject. We now have the centrifugal force. So we're just going to substitute. T1 is already given our maximum allowable tension. So we're just substituting. That's T2 is equal to what? All right, so let us substitute the first one, T1, our maximum allowable tension. Remember, it was given as 900. All right, guys, if I keep on coming up and down, this board will end up dragging and I'll lose this class. So let me just, okay, 900. And our TC is what? This one, don't forget your TC. So we're just going to substitute these values. All right, so this is 900 minus TC. Remember, it was 277,584. Everything over e to the exponent of micro. This is the coefficient of friction. Remember, our coefficient of friction is 0.3. The coefficient of friction here is 0.3. And our theta is the contact angle. You take it in radians. This one, theta. You take it in what? In radians. So it's 0.3 times theta. That's the coefficient of friction, 0.3 times the angle of contact in radians, 2.792. Now let's go to this cosec. Remember from our mathematics, the cosec, the ratio of the cosec of alpha, if it is x, it's 1 over the sine of x. So if it is alpha, it is 1 over the sine of alpha. So in order for you to access this on your calculator, how do you write it? It is going to be 1 over the sine of alpha, the ratio that corresponds to cosec. It's 1 over sine. So this is 1 over the sine of alpha. Remember, I said this is taken in degrees. You take it in what? In degrees. So meaning to say here, we got 23 degrees. Remember, it's the half groove angle. That's why we divided by 2. 46 divided by 2, and we got what? 23. So this is sine 23 degrees. All right. So this is, we are going to add our centrifugal tension. All right. So remember, there's plus TC, whatever that you get here, we are going to add our TC. Remember, this is our TC, which is 277,584. All right. So that is our T2. We need this T2 in order for us to use it there to calculate our number of VBL. So it's still there. We are still there. All right, so I want you to see this here. I'm just gonna need a calculator. There's a lot of information here. I'm gonna end up losing you guys. So let me just try and have this on my calculator. I'm just hoping to win. I'm just hoping to win. I now have a lot of information. So this is, just put a fraction here. We're gonna have 900 minus this. All right. So the first part of the fraction is not that difficult to most of us. Just gonna substitute minus 277,584. Okay, then this is over E. This E is the Napierian log, the base of a Napierian log, this one, the E. So it's shift, you go to this E, like that. All right, so that's 0,3. Already the exponent was there when you put this E. So you just multiply 2,792. All right, times the moment you use a trig like this, it's a trig, this one, a trig ratio, 1 over sine is a trig. It's in degrees, so your calculator must be in degrees. So it's 1 over, so that will be 1 over the sine of 23 in degrees, the sine of 23 like this. Then move aside, all right? This is here, we have to move again, we are here now. We have to move again. We are now here. So you can add this one, the 277, this value, whatever that you have here, 277,584. All right. So this is what we are having in this case. And let us see what we are going to have. 350,546. So you can even fix this to 3 decimal places. Shift, set up. Then we go to the fix on number 4. All right, on number 6, sorry, you press 6. Then in order to fix to 3 decimal places, you're gonna press 3. Then that is to 3 decimal places, 350,546. So this is our T2. But someone is asking, why are we even calculating this? Okay, do not worry. We are now almost there. All right, this is 4.6, sorry. This is 4.6 in Newton. We are almost there. Like I said, we are almost there. Now let us go back here. We calculated T2 through this whole part of our ratio between T1 and T2, including what? The centrifugal tension. Okay, remember here we said, in order for us to calculate this N, we are going to need this formula P, which is this formula TE times V times N. And in order for us to have N, we're going to divide by TA times V. In this case, divide here by TA times V, which is the velocity. We've got the number of the V belts. So in actual sense, the number of the V belts is equal to the power that we are given there. We already have that power. But over what? Over now, this one is the most important part. That is why we were calculating T2. It is because here we said TA is T1 minus T2. T1 minus T2. So it means in this case to find TA, it is the difference that we have. That's our TA. The difference between what? T1 and T2. So you can calculate these ones aside, or you can just substitute times what? Times the velocity V. We are going to have the number that corresponds to the V belt. So that is the number of V belts is P. Our power, that is 30 kilowatts. So this is 30 times 10 to the exponent of 3. Everything over what? We're going to have the difference between T1, which is 900. So let us just substitute here. Remember, we calculated this T1. T were given. And we calculated T2. From this calculation, remember our T2 is 350,546. All right. So this here, we're going to multiply by the velocity. Okay, guys, I think here we now have this. I'm just going to remove this. Like I said, guys, if I end up with a lot of information, these boards, they tend to misbehave. So guys, you must understand this. All right. So anyways, let me multiply this to the velocity. Okay, our velocity, we got it here. the velocity here, 23,562, 23,562. All right, that's 23,562. Okay, so this is 23,562. So like this, we are going to have the number of the V-build. So this was going to be 2,317. But approximately, we're talking, say, how many are they? So this is approximately going to be to two, say just two, all right? Belts. So we've got two belts. These three cannot change this. We can only change if it is bigger than or equal to 5. So it can change this to 3, but this one is less than, so it cannot change. So you approximate or you round off to the nearest whole number on that one. So this is how you're supposed to have this question. So I want you to correct that part. Like I said before, it was just an error that they did not consider a lot of things there. So just be able to do so by correcting this. All right, so this is how your questions sometimes might be given. So you need proper information to answer the question. All right, you need proper information. That was actually 14 marks there. Okay, let's see. We are given fig 1 below shows the setup of a cutting tool held in the tool holder of a shaping machine. All right, so there we are given a shaping machine. That's the cutting tool here that is held together, the clamping screw, and also the cutting force, which is F1. All right, I mentioned about this before, so we're not going to waste much time. Let us quickly check out the questions we're given. So here we were given the first part, that is the ram of the shaping machine is a mass of 150 kilograms and is operating with a cutting stroke length 150 millimeters. All right, so there we are given the mass of 150 kilograms. All right, so let's take note, the mass of 150 kilograms, the stroke length of 0.15 meters. If we divide this one by 1,000 to meters, the total work done during the cutting stroke is equal to 175 joules. So we are given the total work done there. Take note. Remember, when we are dealing with the metal cutting machine, there are different types of work done. We've got the cutting, we've got the frictional, and we've got the total work done. And we have to consider those three. And the friction between these is 0.3, which is the coefficient of friction. The coefficient of friction is 0.3. So this is what we are given. Then the question is asking us to calculate 3.1, the total work done to overcome, the work done to overcome the friction between the ram and the slides. I was surprised because already they gave us the total work done. So here they want us to calculate the friction to overcome what? The friction. The work done to overcome the friction. So how do we calculate this? Remember, I said all these formulas before. So the work done to overcome friction, we said this is the frictional force, which is the horizontal force times the stroke length. Where are we having this frictional force or this horizontal force? From the coefficient of friction. Remember that it is equal to the frictional force or the horizontal force over the vertical component, which is our normal reaction. So we can calculate this. This is over 1. So if you cross multiply, that will be the frictional force, which is the horizontal component, or horizontal force, is equal to the coefficient of friction times the normal reaction. And we know that the normal reaction is the vertical one. So if we are talking about the vertical one, we are talking about the mass times what? The gravitational acceleration, the force, the weight component. Mass times what? The gravitational acceleration. So that means this can be given as the frictional force is equal to the coefficient of friction times the mass times the gravitational acceleration, representing our normal reaction. So let us substitute this, and we can even substitute everything there, or you can calculate this aside. It's up to you. 0.3 for the coefficient of friction times the mass of 150 kilograms times the gravitational acceleration 9.81. Thus, we are going to obtain, that was 441.45 in Newton. So with this, we can be able to calculate the work done to overcome this friction. Remember, work done, force times distance, does not change, force times, but which force? Work done for friction, force for friction. That's the case. We need to force for friction. So that is 441,45 times the stroke length, which is in meters, 0,15. So that was going to give us 66. All right, 66.2175, which is 218 to 3 decimal places in joules. So this is the work done to overcome friction. Let us just put it aside here. We might need this. Remember, there's that formula that consists of the total work done and that of the frictional force and so forth and so forth. And the one for the cutting, yeah, we must have the one for the cutting work done. So all those, you must be able to know them. All right, let us check the part here. That is the one they are asking here. All right, they are not actually asking the cutting work done, but the cutting force. 3.2, the cutting force exerted on the cutting tool. So remember there we are given a cutting tool. If we are to check here, we've got the cutting force, which is F1. So they want us to calculate that cutting force, okay? So how do we calculate the cutting force from the cutting work done? All right, so this is 3.2. So let us see here. 3.2, we need to calculate the cutting force, and this is supposed to be taken from our cutting work done. Each and every work done was taken from its own force. The cutting work done is taken from the cutting force times the stroke length. So meaning to say, if we want this, we're just going to divide by the length, divide by the length. But do we have the cutting the work done to overcome the cutting force? We do not have the cutting, the work done cutting, or the work done for cutting. We do not have that. We do not have that, all right? So we need, this is F. So we are remaining with F here. This is F. So we do not have this. So where are we going to have this? All right, remember that these two together, they give us the total work done. The total work done is a combination of these two. The total work done, or work done total, is the combination or the sum of the cutting work done plus the work done against what? Against friction. So that means as we need this so that we'll be able to calculate the cutting force. So what are we going to simply do? Transpose this because we have it. We calculated this before. So that's our work done total minus the work done to overcome friction is the work done cutting. So we can have this, just substitute your values. So our work done cutting is equal to the work done total, which is 175 minus the one to overcome friction, 66.218. And that was going to give us the difference of 108,782 in joules. So this is our work done cutting. With this, we are able to calculate our cutting force. So the cutting force is work done cutting 108,782 joules over the stroke length that we are given here, the stroke length of 0,15. All right, that's 0,15 in meters. So we are going to have the cutting force. So that's how they play around with this. So the cutting force is going to give us to 3 decimal places. That is 725,213. I showed you guys how to use your calculator to convert your answers to 3 decimal places. All right. So with this cutting force, like I said, it is the one that you're given here on this diagram here. It is the one that you have here. So it means the force here is 725,213 in Newton. That is what you have there. Okay. Anyways, let us see what we are given on the other part. If we are to check here, this was, okay, so this one we are done here. This one we're done. All right, 3.2, we are done. 3.3, they want us to calculate. Take note here. Our question is the forces exerted at the what? At the contact points A and B if the clamping force in the screw, in the clamping screw is 2,000 Newton. 8 marks for that. How so? So we need the forces that are at point A and B. All right, let us get back here. This is our point A, the point B. All right. I said on this question, guys, go back to your science, engineering science N2 actual. All right. From our science N2, we understand that here we can use the moments there. Look at this diagram, how it is like this. All right. Just bring it down. All right. Just take it down. I hope I can just shift, like I can turn the screen of my machine so that you see what I'm trying to say. But just bring this down. You see that you've got something of this, just a length like this. This is our length. All right, having a force at the end, which is our cutting force F1. So there is a force here at the end of our point here, which is our F1, which is our cutting force 725,213 Newton. All right, then from this force here, which is at the end, there's nothing here. There's a distance in between up to the point A. So there is a distance here up to the point A. So we have got a point that is at A. All right, we've got A here. So this A is actually a support. It's going up. All right, A and B, they are supporting up like this. A and B, these are the supports. These are the point loads, these two forces that we have are the point loads. So in between this, there is a distance of 75. All right, then between A and B, there is 65, 65. So take note here, we are going to move a certain distance. All right, that is something like this. We move a certain distance, then we move again a certain distance up to the support at B. B is the support. So this one in between here that is separating A and B is this one, the clamping force, this one, and the clamping screw, this one. So it is, you take this as it is, the 2000, it is one entering straight halfway. So there is a point load. Remember, guys, your moments, all right, from your science N2. So this is at 2000. So there is a force there of what? Of 2000 Newton. All right. So like I said, or like what we are given here, there's a distance 65, 65, which is equal 65, 65, just like that. So it is ending there. There's nothing to consider at this other side here. There's nothing to consider. Like this is enough. So guys, these are moments. We want to calculate the force at A, the force at B. Guys, what does our moment say? Depending with what you have, let's say I've taken my moments about A, or I've taken, about B or about A, it's up to you. So in this case, I'm gonna use, I'm gonna take my moments about A, taking moments, all right, about B. So guys, let us go back to our science N3, N2, N3, yeah. That is N2 actually. All right. So if we take moments about B, we are going to see that A, as it is moving back to B, it is moving this way. And what is that direction? That is the clockwise direction. And this is anti-clockwise. So this is moving this way, clockwise and anti-clockwise. All right. So we are going to see that A is moving in the clockwise direction. What about F back to B? F is moving this way, this force here back to B like this. This is like this, anti-clockwise. So this one is in the anti-clockwise. What about this one back to B? It is also anti-clockwise. So this F1, as it is moving back to B, it is anti-clockwise. So we only have one clockwise. So as we know, guys, the sum of the moments that we have in the clockwise, like the sum of moments for the clockwise is equal to the sum of moments that we have in the anti-clockwise. So for the clockwise, we just have A back to B. Remember, we said we are taking moments about B. So A back to B is going to be force times the distance back to B. Remember, guys, like I said, our moments, the whole distance between A and B is this one. So you add 65 plus 65, which is what? 130. So that means it's going to be force times distance. That is A times 30. Is there any other part in the clockwise? No, there's nothing. It was just one, this one. The A going to what? The A going to B. The rest, they are in the anti-clockwise. Which one? The 2000 back to B. What is the distance there? 2000 force times distance. The distance back to B is 65 meters. All right, which other one that we have in the anti-clockwise? We also have this F1, our cutting force there, going back to B. That will be 130 plus 75 you add. So 130 plus 75 is what? 205. So this will be 725, 213 times 205, the whole distance back to B. So this is your moments, guys. There is nothing about cutting machine there. It is your science. Okay, A times 30, that is 30A, is equal to, you combine everything on the right-hand side. This was going to give, guys, is this 30 or 130? 130, 65 plus 65, 130, 130, this one. This is 130. All right, you add everything. On the right-hand side, we are going to have 278,668,665. All right, so if we divide by 130 both sides, divide by 130 both sides, we have the value of A, the force that is operating at point A, and that was going to give us 2,143,605 in Newton. So that is what we have at what? At A. So guys, we know that these are moments. So instead of me going back and taking moments about A again, yes, we could have taken moments about A, we calculate B. But after calculating one of these, try also to apply also the law of the forces. What do we understand about the forces? We understand the sum of the upward forces should be equal to the sum of the downward forces. The ones going up is what? It's A and B. So if I add these two, the supports A and B, they must give me these ones that are going down, which is this one, the F1 there, and the F there for the clamp. So I need B because I calculated A. So I'm just going to take A to the other side. So it's going to subtract. So B is going to be equal to F1 plus that F minus A. So that's, I can have B. The F1 is the one of the clamping, this one, which is 700. Remember, it was 725, 21. Is this 213? Yes. Plus F. The F is 2000. So this is 2000 minus A. A is the one that we just calculated now, which is 2,143,605. So combining this together, we have our B. So this was going to give us 581,608 in Newton. So that was the idea of the question. That was the idea of the question. So just check more questions under this channel. You'll see that we have got a lot of part that we have done or that we have covered about this part of the metal cutting machines. So just check other questions also that can help you in answering questions, and do as many questions as possible. Do as many questions as possible. All right, so that was the end this question. 14 marks for everything. Then question 4. Question 4, what are we having here? We are given a V groove. All right, so we are back to our precision measurement. Fig 2 below shows the workpiece with a V groove, which is an angle of 60 degrees included angle, which is the included angle, and a depth of 50 millimeters. All right, so no problem. Refer to the fig 1, that is to fig 2, this one, all right? Above, name the numbered components, write only the answer next to the 1, 2, 4. All right, the components here, what we have. So remember this. For the fourth part is the V block. This one is just going to be V block, the roller. We also have our gauge block. That's our gauge block there. All right, got the gauge block, and one, which is the straight edge. It's a straight edge, this one. It's straight edge. All right, let's hope I talked about this. So you just need your diagram and so forth. I think this one, guys, you can just recall from your theory. I'm worried about this question here. Use fig 2 to calculate the distance h. All right. There we have got 6 marks. use fig 2 to calculate the distance h. Okay, let's hope I'm just gonna win in this presentation here. All right, let us take a closer look on our diagram here. All right. Already they did us some constructions here. H, this is our H here. This is where our H is. All right, they're indicating here in between. So this is our H. So if we are to consider this, all right, like I said, let's hope I'm gonna win. I'm going to win. Let's hope so. I needed just a line, guys. Okay, just a line. Maybe I'm just gonna win here. All right. So this is it. If we are to consider the wall of this line from this point here, from this point, going down, going up to this point, straight up to this point. The problem is that this centimeter that they are showing me there, I don't like that. It seems that, okay, it does not seem like it is exactly what we have there. It is this point at the end. We take it straight like this, straight. So it means that this distance is the whole part of this. It comprises of these two, the h and the 50. So let us just name our points. Let us just say this is A to the center. This is our center here. So let us just name our points and say this will be the point A here. Okay, this will be our point B. And at this end, this will be our point C. So what does it mean? It means if I add this whole part, if I take this whole part of AC, it is equivalent to the wall of this line, like as you can see, from H up to this one. So it is the combination of the H and the 50 millimeters. So this is H plus 50. All right, guys. All right. There we have got the diameter of 40 millimeters. Given a diameter of 40 millimeters, it means our radius, that's d/2, which is 20 millimeters. Why am I talking about the radius? From A to B, that is our radius, okay, which is 20 millimeters. Okay. We need to find H. Okay, by the way, let us just make H the subject. Take this side. So it's going to be AC minus 50. So H is equal to AC minus 50. So we need to calculate AC. That's why I'm focusing about this. So to find AC, it's A to B, this one, this AC, this one. We need that. Guys, are you following? Are we just together there? That we need AC. Are we just together there? Okay. If we are together here, I'm saying here that AC is equal to what now? That is the combination of these two on the circle. We consider from A to B, that is the part of the radius. Okay, that is A to B, which is our radius. Plus from B to C, as you can see from B to C, we are now out of the circle. We have exceeded the circle. So it's no longer the radius. No, it's no longer the radius. From B to C, the radius is from B up to here. From B up to this point. Yes, this one is the radius. But take note, C is extended there. So how do we take advantage of this? Because we do not have this, because I said AC is equal to AB, and we agreed that AB represents the radius. So this is our radius, which is 20. We already have this. Plus BC. We do not have BC. So it's a step by step. I do not have this. I have to find that. Okay, let's think of calculating BC. Okay, if you check your diagram properly here, this is our line BC. Okay. This is a circle. Let us go back to our mathematics. A circle and a line where they meet like this. A line which touches a circle is called a tangent. This one. It's a tangent. So what happens is that if you draw from the center to the tangent like this, from the center to the tangent, you form a radius. Yes, but it is at 90 degrees. The same thing that we are having here. Okay, anyways, from the center to the tangent, anyway, from the center to the tangent, this is our radius here, but it will be at 90 degrees. at 90 degrees. Take note, at 90 degrees. So if it is at 90 degrees, what is the advantage? Remember, we want to have an expression for BC. So we can take advantage of that because there is a 60 degrees. From our groove angle here, it will be divided into 2 equal parts. So 60 divided by 2, it will be 30 degrees, 30 degrees. And from our mathematical knowledge, we know that these are vertically opposite angles. So if this angle is 30, it means also inside is going to be 30 degrees. And this one will be also 30 degrees. So I want you to take this right-angled triangle from B to C. Remember, we want to find BC. So let us just call this point D. All right. So I want you to take from B to D. Remember, it's a right-angled triangle like this. I want you to see what you're formulating there. This is what you have. All right. This is our B. This is our D. And this is our C. This is what you're formulating. So this is a right-angled triangle. Remember that. It's a right-angled triangle, this one. It's a right-angled triangle. And there is an angle of 30 degrees inside the triangle here. There's an angle of 30 degrees, this one at C. So I can use that to calculate this BC. Remember, we said BD, this one, from B to D, is the radius, this one, which is the radius. Remember, it was what? 20 millimeters. We know this one is 20 millimeters. So we can calculate BC. How are we going to calculate BC, guys? That is the question. How are we going to calculate BC? How are we going to calculate this BC? Because we need the BC here. We need the BC here. So BC from this part, if we take our triangle, we can see that according to theta, this R that we have is the opposite. Remember, you use what you're given. What you're given is opposite. BC is the hypotenuse. Which ratio uses opposite and hypotenuse at the same time from our trigonometrical ratios? So katoa. So opposite and hypotenuse, that is the sine. So it means the sine of theta, the sine of 30 degrees is equal to the opposite, which is BD, the radius of what? Of 20, over the hypotenuse, which is BC. So that's it. We want to calculate BC. We're going to cross multiply BC times the sine of 30 degrees is equal to 20. So if we divide this by the sine of 20, it's going to be BC is equal to 20 over the sine of 30 degrees. So this was going to give you 40. From your calculator, you're going to have BC as 40 millimeters. Remember, these are millimeters. So we now have BC. We're just going to substitute here to find AC. Remember, we want to find AC. So AC is equal to the radius. And our radius is what? Is 20 millimeters plus BC. BC was from the diagram. The diagram is the one that helped us to calculate this. So from our diagram, we now take our BC into consideration, 40 millimeters. So guys, there are so many ways. These are mathematical calculations. There is no one way to say you are supposed to follow suit like this. No, these are mathematical calculations that you're now taking. As long as it's a shape, use your geometrical concepts. Everything about your geometry, as long it is useful, use that. You are going to find this. All right, so let us find our AC. So our AC is going to be 60 millimeters if we add properly. So by finding AC, automatically we have the height. Why? Because we said the height is equal to AC minus 50 from that ratio. I mean, from this equation that we generated before. So it's just a substitution that we are simply making. Remember, we calculated our AC and got it as what? As 60. So this is 60 minus 50. So H is going to be 10 millimeters. So that was our H there. Just like that. Just like that. So there can be so many ways of working with this. We just hope with time, we are going to do all those things. Describe how you would test the magnitude of the angle on the workpiece. On this workpiece, describe how do you test the magnitude of what? Of the angle. All right. So there we are given, it was remember we are given there this was 40 millimeters, the diameter, it is 40 millimeters. So that's why you're given plus the 40 millimeter diameter precision roller gauge. Then you set up 2 sets of gauge blocks exactly 10 millimeter thick. Then place a set of gauge blocks on either side of the groove and place the straight edge on top. The angle of the groove will be correct if the 2 sets of gauge blocks each having a thickness of 10 millimeters and a straight edge touch the top of the roller. So this straight edge, it must touch the top of the roller. All right, so that's what we have there. For 4 marks, I think, yeah, you can just sacrifice to write all those. Yeah, you can have that. Maybe you're at 46%, you need 50%. 4 marks is actually important. Or maybe 36, you need 4 marks to get 40. So guys, don't hesitate to work on this. It's very, very important that you do revise along the lines. You do revise along the lines. All right, so this is question number 5. Let us check question number 5. So on this question, if you check, it was already an advantage. They tried even to give us how this presentation looks like on this side. But you are supposed to know what is the presentation there. So we are given an epicyclic gear train as shown in figure 3 below. Then we've got the gear wheel D. It rotates at 100 revolutions per minute. All right, that is the gear wheel D. Remember, D is connected here. So this is connected at 1000 revolutions per minute, all right, which is the speed of D. Then we are given gear B and C are keyed to the same shaft. All right, so if we check here, this is our C and this is our B here. So these are keyed to the same shaft. All right, so take note about that because it is important when you are talking about what we refer to as the aligning gear. All right, when we're talking about the one that is in line, which is our gear C, which is in line with the B being what? The planetary. All right, so remember I talked about these gears, everything here. So let us just see what we have in this case, So let's start with A here, which is our annulus. So remember that A represents our annulus. Then B is the way here, which is the connection of this C, is our planetary. So B is our planetary. All right, remember, we need to have the annulus, all right, which is at the end, which is our B. Then the gear C, this one, the part of C is just in line with B. So this one is just in line. All right, then we also have the sun gear. This one is our sun gear, which is D. So we have the sun and E is the arm. So this is what we have. I think everything is listed. So that is the idea there that we have. So remember on this part here is our sun gear. So meaning to say we have got our D here. This is our sun. Okay. Then the arm, the planetary. So we've got the planetary here, which is P, our planetary. All right. So meaning to say we are talking about the planetary gear on this one as the gear. So this is our planetary gear. Then the annulus, like I said, which is our B, the annulus. So you are supposed to know this diagram. So the question was that determine the speed of gear, the gear wheel A. If A is stationary, then the 5.2 determine the speed of E if gear A is fixed. So we are going to answer this on a single diagram, but separate our questions later on. But this, we just put it on a single diagram. So these are the, this is the information that we have, and we've got 4 gears to be considered. That is gear A, the annulus. That is what we have in this case. All right. Why am I writing B here, guys? This is A here. A, we said B is the planetary. planetary, which is B. All right. Sorry, guys. A, B, C. All right. C is the incline, which is with B, and D, the sun. Okay, so this is it. So you are going to see that on your table, I just took this part, gain aside. All right. Just hope my table, guys, I misplaced my table here. All right, so let me just try to put this table here. I'm not gonna waste much time. I'm just gonna use this table, guys. Very sorry for that. As for this one, guys, I'm very sorry. I'm just gonna take this table, work with it, because it's gonna take us a lot of time for me to reconstruct this thing. All right, so this is what we are having here. Remember, I said before that this one, you just have to follow your stages. All right, so these are the gears that you're gonna have. According to this part, we've got A, which is our annulus. Remember, we said A is representing our annulus. Then B is the planetary. Remember, I listed this. This is our planetary gear. Then the gear C is just in line with our gear B. Then D is the sun gear in this case. Then we've got the arm. All right, so the first condition, like I said before, that we are given, our first condition was to fix the arm. You have to fix the arm. You rotate gear A by 1 ripple. It's a fixed thing that you're supposed to know always. There is no way you're going to go through rotate minus 1 ripple. It's always you fix the arm, you rotate the annulus. You fix the arm, you rotate the annulus. It's always like that. So the annulus is our gear A, so it's just going to be a +1 revolution there. Then on the planetary now, which is our B, this is our B here. What's going to happen as we rotate A, as A is going 1 revolution in the clockwise. What is going to happen with A? So we are going to say A is going to be affected by B. So that's where we see it's going to be the number of the driven, which is in this case is going to be TA over TB. All right, so it's TA over TB in that case. So this is TA over TB. And also these ones, you're just supposed to know the formulas. I think I listed about this, and it's always a positive. This one, they are all going in the clockwise. So A is what before the teeth that we have on A. Remember, we are given A here 100, and B is 16. So this is 100 over 16. All right, so that's what we put 100 over 16. So if we're to divide this, we're going to get 6.25. Then C is in line with B. So we saw that. So this is just going to remain as 6.25. There's no need for you to calculate that. Then you move on to the D, which is the sun gear. So D is the one that is in the middle, this one. So it's a combination of two, affected by the movement that is happening between the annulus and the planetary, and also the movement that is going to happen between B and C, that alone, the B and the C. The B and the C. So in this case, we're taking B and D. So it's going to be like this, the formula. Remember, this is moving with a positive TA over TB. It is affecting our gear, and also affected by TB is, if you check, it's now a connection here of what? TB and what? B and D. So B is moving D. So it's going to be B over D there. So you multiply TB, but D is now rotating in the negative. So meaning you say it's going to be a negative. So this one was simply going to be TC, because remember that TB and TC are the same. So you can also use TC here. That's the idea. So just leave the formulas there. So this we already calculated 100 over what? Over 16 times TB. Remember our B is what? It's 100. Then D, it's a negative. If we check, D was what? D here is 28. So if you check the D, that's a 28 there. So that is the idea. So I think this one, I wonder, you guys, you say this is the hardest part, but I think this is the easiest part, because there you just follow suit. You just follow. Remember, the arm is what? Is fixed. We fixed the arm, so there's no movement. There's just a 0 there. The arm is fixed. It's stationary. There's no movement. All right, so once you fill in the first part, if the first part is filled, the rest is just what? Is just a follow suit again. How do we fill in? We're going to multiply by x, then we add y. Everything that we have here, we multiply this by x, so it's 1 times x, which is x, then we add y. You multiply this by x, 6.25x, then we add y. Again, this by x, 6.25x, so it's going to be 6.25. Sorry for that. 6.25x plus y. The same here by x, minus 4,911 times x plus y. 0 times x, that's a 0 plus y. So it's just going to be a y there. Okay, so that is the idea there. So we have this. Then, as I said, we have got 2 questions to answer there. Question 5.1 and question 5.2. Remember, these are 2 questions that you're given here. So on 5.1, they are saying we need the speed to determine the speed of the gear with the speed of A if E is what? Stationary. Take note, these are conditions. We must find the speed of A. We do not know this, but given that E is stationary, so if E is stationary, it means there is no movement there at E, it's a 0. But which other speed are we given? Remember, previously we are given something that will never change, which is the speed of what? Of this D here, which is our sun, D. It is what? 100. So this is going to remain at 1,000 I mean. So that one is going to be there for all conditions. And D is going to be 1,000 revolutions per minute. This is the information that we have. Even when you are to answer question 5.2, ND is not going to change. It will be remaining at what? It will remain at what? At 1,000 revolutions per minute. So you want to calculate A. That is on 5.1. They ask you to calculate the speed for A. So you do not know that. Given that E is fixed, which is the arm, so the speed of E is 0. There's nothing there. So how do you calculate this? All right. So you are going to just put in this A. Remember, A is the one that you want to calculate. So this will be N. A, want to calculate the speed of A. B, do we have anything for B? There's nothing. What about for C? There's nothing. What about for D? D is what? 1,000. That is the speed there. What about the arm E? The arm is fixed. So there's no movement. That's a 0. Just like the first case when we fixed the arm, there was nothing there. It was a 0. So it is the same thing. The arm is fixed. So that's a 0 there. All right. Then on 5.2, it's another question. So this you can calculate your 5.1. You move on to 5.2. So 5.2, they are now saying, this time you have to calculate the speed of the arm when A is what? Is fixed. So we want the speed of the arm. Remember, the arm, it's E. We want the speed of E. We do not know. But A, it's what? A is fixed. Whatever that is fixed, it's at what? At 0. That's the condition of question 5.2. That's the condition of question 5.2. So this, you are going to use it to answer question 5.2. So the speed of A is the one that you're given. Remember, this is A. The annulus is the one that you're given as 0. It's fixed. What about B? There's nothing. What about C? There's nothing. What about D? D is not changing. D is still at 1,000. While least we need to find the speed of the arm, which is our E at the end. Here we've got what? E. What do we have at E? That is the one that we are supposed to calculate its speed at the end of the day. So that is the condition. So this part here is for 5.1. This one. We use it to calculate 5.1. So for question 5.1, we are going to equate whatever that we have here to these values in 5.1. So this is it. What this part that you multiplied by x, then you added y, is the one that you equate. You are equating to what? To 5.1. Remember, I said 5.1. So we are equating to this on 5.1 here. This is what we are equating to. So this must be equal to this. All right, x plus y must be equal to what? To NA, the speed at A. So x plus y is equal to NA. So to find the speed of A, we must find x, we must find y. Also, this here is equal to 1,000. It's an equation that we have there. Minus minus 4,911x plus y is equal to what? To 1,000. Also, y is equal to what? To 0. We are equating what is on this column for question 5.1. This is the column, this is the condition that we were given for question 5. So you are dealing with this condition. We are answering question 5.1. So on this part, you are already told that y is a 0. So that's a 0 there. So you can calculate what? X. So it's simply going to have minus 4,911x is equal to 1,000. These are now equations. Divide by minus 4,911 by negative 4,911 like this. You are determining or obtaining the value of what? The value of x. All right, so that was going to give us the value of x, which is negative, that's a negative there, negative 203,625. But like I said before, that the speed at A is x plus y. So therefore, the speed of A is x. We got our x as what? Negative 203,625 plus the speed at A, plus y. Remember, y is equal to 0. So thus we have NA, which is negative 203.25, just like that. So we've got a negative speed there in revolutions per minute. So the negative simply shows that this is what? An anti-clockwise direction that we are talking about there. It is moving in the anti-clockwise. So we've answered question 5.1. So question 5.1, it was a condition for calculating the speed of A. So 5.2 is the one for E. This is the condition for 5.2. We use this condition now, this one, that we have for 5.2. So meaning to say we are no longer considering what we had on A. This was for A. It's no longer valid. It was used. It's no longer valid. This is no longer valid, this part. We are now focusing on question 5.2, where we need to calculate the speed of what? Of the arm. This time we need the speed of the arm. So to calculate the speed of the arm, we do not know that. We do not know this, the speed of the arm. We do not know it. But what we given in terms of our equation now, just like what we did, this time we are equating to 5.2 to this one. This is where we are equating. What are we equating? Those x and y that we had before. X plus y must be equal to 0. That is what we have. It's an equation there. X plus y must be equal to 0. You move on to another part of x and y. Here, there's nothing to equate. There's nothing here. So you move on to this one. It must be equal to this. So minus 4,911 x plus y is equal to what? To 1,000. Then the last part is this one. Y is equal to what? Y is equal to NE. That is, if y is equal to the speed of the arm, which is NE. So it means to find NE, we simply need to calculate the value of y, because they are saying y is equal to n. This is what we have from our diagram. So by solving for y, we are solving for what? We are solving for NE. It helps you a lot to know these mathematical situations, because you are not going to calculate x here. Why? Why are you calculating x? For what? We need only y. Remember, these are simultaneous equations where I can solve any letter that I want. So if I want to calculate y, I can just make x the subject from one equation. If I make x the subject from this equation 1, it's going to be x is equal to y to the other side is going to be a negative. That's 0 minus y, which is what? Which is minus y. So from this equation, it means wherever I see x in the other equation, in the second equation, I'm going to substitute minus y. That's from this equation, we're going to have minus 4,911 times the value of x represented by what? By a negative y. Plus y is equal to 1. Remember your substitution method. To eliminate x, to remove, x, you have to make it the subject from another equation. Then you substitute it in terms of y. You have removed x. You are just left with y because you want to solve for y. Only y. All right. So this is you guys again. with your mathematical calculations, so this will be a positive here. If you multiply negative, negative, so that will be 4,911y plus y is equal to 1,000. That's a 1. So if we add, this will be 5,911y is equal to 1,000. So if we divide by 5,911, we were going to obtain the value of y in this case. So thus, in this case, y was going to give us 169,176, and that's a positive value. So in terms of the speed, therefore, it follows that the speed of the arm is going to be equal to the value of y, which is 169,176 revs per minute. Remember, this is speed in revs per minute. And that's a positive to show that this is clockwise. So you're going to write it as a positive. That's the idea there. That was the idea of the question. So like I said, the table, we used it at once. We drew our table at once. We just have to draw this. You just have to draw it at once. But when answering your questions, you are separating. There's 5.1, there's 5.2. Okay, thus here we're gonna have this other part of question 6. So let us just try and see. That was hydraulics in this case. 14 marks again, hydraulics. All right. Water with a density of, take note, water with a density of 1,000 kilograms per cubic meter is pumped through a vertical pipe that is 15 meters long. The tapered pipe, there. It's important. It is a vertical pipe, yes, but it's a tapered one. All right, guys, you know, guys, to understand is very, very important. Just to understand is very, very important. So when this is a tapered type pipe, it means that we are going to have something of this nature. It's a vertical one. So you're going to have the top with a bigger diameter. As it is going down, it's going to reduce in terms of the diameter. All right, so that's something like this. So guys, to record full papers, it's a disaster. You know, these machines, they are very, very, I mean, these softwares, they are very, very tough to operate with. But I'm just trying, guys. Let's hope it will be clear to you. It will be clear. All right, so this is what we are having, guys. We are having this as a vertical one. So we've got the vertical height in this case. So we are given that it has got a density. In this case, we are given the density of 1,000 kilograms per cubic meter. It is pumped vertical, 15 meters. So this is the height of the given pipe. And it has a diameter of 180 millimeters at the upper, at the top. So the bigger diameter there, divide by 1,000, that will be 0.18 meters. Then 100 millimeters at the lower end. If we divide this by 1,000, that will be 0.1 meters. So there are two different diameters. Then we are given when 90 liters per second, 90 liters per second. What is it? This is the flow rate, 90 liters per second. Remember, I said a cubic meter is equal to 1,000 liters. So if we are given 90 liters, it means we have to convert to cubic meters. Divide this to 1,000. 90 divided by 1,000 is going to be 0.09. That's cubic meters per second. So we've got the flow rate there. All right, that is it. What we have is pumped upwards through a pipe. A reading of 230 kilopascal is registered. Where? At the lower end. So at the lower end, we registered, or there was a pressure of 230 kilopascal. And the question is, we are supposed to calculate the pressure gauge reading at the upper end of the pipe, at the end, at the upper. So this is the 0.1, the 0.2 at the upper end. So this is it. Using or applying our Bernoulli, which is from our Bernoulli theorem, we understand that from our Bernoulli theorem, we understand that in terms of the formula, all right, this is our Bernoulli, guys. Our Bernoulli theorem is states that, remember, that's where we have P1, P2, this and that. We says that P1, pressure, that is density times gravitational acceleration, plus V1 squared, which is the velocity there, over 2G, plus the H1 for the height is equal to, you just take these and put this side with 2. Just put 2. So it's going to be P2 over density times gravitational acceleration, V2 over 2G plus H2, just like that. So we've got pressure 1 already given. This is the P2 that we are supposed to calculate. So we need to calculate P2. So let's check. We need to calculate P2. We are given P1. V1, we do not have velocity. So we are going to use the flow rate to calculate V1 and V2. We need to calculate this V1 and V2. What about H1? H1 is taken at the beginning. This is the point 1. At the beginning here, the height is at what? At 0. We are starting here, so that H1 is at 0. And H2 is now at the end after moving the total height of what? Of 15 meters. So H2 is going to be at 15 meters after covering 15 meters. Then this is your density. Rho is your density. We have it. So as you can see, the only thing missing is V1 and V2, which is of our velocities. So our velocities from the flow rate, we know that Q is equal to area times the V1. That is area 1 times V1. If it is for 2, it's going to be like this. If you're using 2, it's going to be Q is equal to area 2 times V2. So this will be V2. So we know that area 1 at the base here, there's a diameter, it's a circular one. So area 1 is going to be pi d squared over 4, which is pi d squared over 4. This is D1. So D, this one is a smaller d. At the top, you're going to use capital letter D, depending with how you write it. So I can calculate V1, representing the velocity, if I just divide by the area both sides. That means V1 is going to be the flow rate of 0.09 cubic meters per second over what? Over the area. All right, so the area 1 at the point 1, we say that's pi d squared over 4. So it's going to be pi times the diameter at this point. That's 0.1 squared over 4. So this is going to give us the velocity there at the entry. So thus we are entering with a velocity of what? 11,459. That is 459 meters per second. So you do the same thing for V2, only that for V2, you are now using area 2. So it's going to be the diameter there is going to be pi d squared over 4. That is the area 2 that you have at the end there. So thus your area 2, in this case, sorry, our V2 just divide by area. So it's going to be A2 over A2. All right, so this concept, we've got the velocity, which is the flow rate over the area 2. The flow rate does not change, 0.09 over the area 2, that's pi times d squared. So the diameter at the point 2 there is 0.18 squared. All right, so that's it. So we are going to have V2 in this case, and that was going to give us 3.537 meters per second. We entered, so it is entering with a higher velocity, and is when it's going out, it is having a lesser velocity. Remember, it's wide open there at the end, so the velocity is going to be less. So that is the only part that was missing on this formula. So since we have calculated everything that was missing, therefore let us substitute into the formula and try to calculate P2. With our P1 of 230 kilopascal, that is 230,000 kilo, that's 1,000, 230,000 over the density. Remember, it was 1,000 kilograms per cubic meter times the gravitational acceleration 9.81 plus V1 squared. So we calculated the velocity, the V1 is 11, that's 11.459 squared over 2 times the gravitational acceleration again of 9.81. So H1, remember we said at the beginning there, H, the height is at 0. We are starting, guys, so the height starts at 0. So this is equal to P2, the one that we are supposed to calculate, over the same thing. Our density is a repetition as the previous case, times 9,81. All right, so this is it here. Then we're going to move on, plus this will be V2 squared. Guys, why am I leaving this? There's a square there. So this is V2 squared, which is this one, 3,537 squared, everything over 2 times G, which is 9,81 plus H2. Remember, I said it's now H2 is taking the whole of this length, the total length that we have there, which is what? 15 meters. So that is going to be your H2. So this will be 15 meters. All right, so I want you to simplify everything here on the left-hand side, everything. So that was going to give us 30,138, which is equal to, so there's a P2 and this one. So let us just simplify stage by stage. P2 over, just multiply these two. 1,000 times 9,81, it will be 9,810. Plus, you simplify these together, that will be 15. If you simplify this properly, you're going to get 15,638. All right, so this is what I did, guys. In order for me to calculate P2, I'm just going to transpose this to the other side so that it becomes a negative there. So I'm subtracting this minus this minus this, because it was a positive. The moment it crosses the equal sign, it carries what? A negative. So I'm going to obtain 14,5, which is equal to P2 over this 9,810. So to find P2, I can simply cross multiply Y. This is single fraction here, single fraction here. So 1 times P2, that is P2 is equal to this times this. So I'm going to multiply 14,5 times 9,810. So this was going to give you P2, the pressure at the exit point 2 there. And that was going to be 142,245 Pascal. So you can convert this because it's pressure. You can even convert to kilopascal if you want. So that's P2 divided by 1,000. That will be 142. So you're going to get 142.245 in kilopascal. So that is how you were supposed to obtain or to have the value of what? Of P2. That is how we're supposed to have this. That is how we're supposed to have this. So you are supposed to understand your formulas. Is it that you are working with a vertical one? Is it that the taper tape is a vertical? Is it horizontal? How are you given it? Is it given at a certain angle, slanted at a certain angle? You need to know your information. So like I said before, we shall have more questions under this platform for our N4 subjects so that you prepare yourselves for the exams ahead, covering our mathematics, our engineering science. Just be prepared to revise with us from Mason African Motives till we meet again.